Hello everybody! In this clip we look at the orbit decomposition of a toric variety arising from a lattice fan, and we study the basic geometry around this orbit decomposition. First of all, we need limit points. So consider a toric variety arising from a lattice fan. Then every cone of the fan defines a limit point. Take any vector from the relative interior of our given cone, look at the corresponding one-parameter subgroup. This one-parameter subgroup has a limit in the affine toric variety defined by the cone sigma. And by construction, this affine toric variety is an open subset of our X capital sigma. So we have a well-defined limit point in X capital sigma associated with this cone small sigma. Here is the orbit decomposition. Consider any toric variety arising from a lattice fan. Then we have a bijection between the fan and the set of all torus orbits in X sigma. A cone is sent to the orbit through the limit point X sigma associated with our cone sigma. Moreover, this bijection is order reversing in the following sense. Consider two cones, sigma and sigma prime. Then sigma is a phase of sigma prime if and only if the torus orbit through X sigma prime is contained in the closure of the torus orbit through X sigma. Let us see what kind of questions we are going to discuss. Look at the blow-up of the origin in C2. This is a subvariety of C2 times P1 given by a binomial equation. And we have a projection map from this blow-up to the first vector C2. As a map of fans, this blow-up projection looks as follows. Here we have the fan of C2. Here we have the fan of the blow-up. And the underlying map of lattices is just the identity map. About this blow-up projection, we know, for instance, that the fiber over the origin is a projective line P1. This was directly computed from the definition of the blow-up in terms of a binomial equation. Our aim is to extract information like this directly from the picture of fans. We are going to look at isotropy groups. First, we need a basic statement on tori. Consider a lattice N, a primitive sublattice N naught, where primitive just means that the quotient module is torsion-free. The inclusion of N naught in N defines a homomorphism of the associated tori from Tn naught to Tn. The fact that N naught is primitive means that this is a closed embedding. Moreover, we can describe Tn naught sitting in Tn as the intersection over all the kernels of characters chi-u, where u stems from the perpendicular space of N naught. We enter the affine case. Consider an affine toric variety arising from a lattice cone sigma in N. We have to evaluate characters chi-u along the torus orbit Tn times X sigma. First, by homogeneity, we know what happens with chi-u of T dot X sigma. This is just chi-u of T times chi-u of X sigma. Moreover, we know already how to evaluate in X sigma. The value is 1 if u stems from the perpendicular space of sigma, and it is 0 otherwise. The next step is to understand when a torus element T fixes our limit point x sigma. This holds if and only if any character function has the same value on these 2 points. By the evaluation rules just seen, this means that T has to lie in the kernel of chi u for all u from the perpendicular space of sigma. This allows us to write down the isotropy group in the affine case, define a sublattice n sigma of n as linear space generated by sigma intersected n. This is by construction a primitive sublattice. Then the isotropy group of the limit point x sigma is, by the previous consideration, the intersection of all kernels of chi u where u stems from the perpendicular space to n sigma. And by the initial consideration of tori, this is the subtorus corresponding to the sublattice n sigma in n. In the general case, that means if we consider a toric variety arising from a fan, computing these isotropy groups, no changes, so we have the same description as in the affine case. In particular, the dimension of the isotropy group at a limit point x sigma is just the dimension of the cone sigma. Moreover, we can say something about the orbit. The variety, the orbit, is the same as the factor group of acting torus modular isotropy group. This allows us, in particular, to say something about the dimension of the orbit. The dimension of the orbit, same as the dimension of the orbit closure, is dimension of Tn, namely dimension of nq, minus dimension of the isotropy group, namely dimension of the cone sigma. So that means that the big cones make small orbits at the end. Next we look to orbit closures. Consider the toric variety arising from a lattice fan sigma and a cone in sigma. Then if we take the closure of the orbit through this limit point x sigma, this becomes in a natural way a toric variety. As a base point we take the limit point x sigma itself, and the acting torus is the factor group Tn modulo isotropy group of x sigma. And the action is defined by letting a class T, Tn sigma act just as Tx. The question is, what is the fan of this toric variety? Here's a concept from convex geometry behind. Consider any lattice fan, then the star of a cone tor from sigma is the set of all cones of capital sigma such that tor is the face of these cones. The geometric meaning of this star is immediate in terms of what we know about the orbit decomposition. Namely, the closure of the torus orbit through x tor consists of all the torus orbits through limit points x sigma, where sigma stems from the star of tor. We are ready to determine the fan of a toric orbit closure. Consider a toric variety arising from a lattice fan sigma and take any cone tor in sigma. The first step is to define a factor lattice n tor as n modulo the lattice n tor. Then we have the projection onto this factor lattice, and this gives us a fan in n of tor, sigma of tor, consisting of all the images P of sigma, where sigma stems from the star of tau. Here's a little picture. This is our cone tau. The star has two more cones, namely those two maximal cones. And if we project along tau, we end up with this fan, capital sigma of tau. And the result is that sigma tau and tau is a lattice fan having as its associated toric variety the toric variety given by the orbit closure. We also look at images and fibers of limit points. So consider a map of lattice fans and its associated toric morphism. First for the images, given a cone sigma, we want to know what is the image of the limit point x sigma. For this, let sigma prime be the minimal cone such that f of sigma is contained in sigma prime. In this situation, the relative interior of sigma is mapped into the relative interior of sigma prime. This allows us to compute the value of the limit point. Take any v from the relative interior of sigma. Then our x sigma is the limit of the associated one parameter subgroup. And applying phi f to this limit means that we have to take the limit of f of phi applied to t dot x prime, and this lies in the relative interior of sigma prime, so that we end up with x sigma prime as the image of our limit point. Now for the fibers given a cone sigma prime in capital sigma prime, then the fiber of this limit point is the following. We know that all the limit points such that the relative interior of sigma is mapped into the relative interior of sigma prime, that they map onto our limit point here. So these points show up here. And what also is constructed by phi f is the inverse image of the isotropy group of this limit point under phi tilde. So this gives us a formula for the fiber of a limit point in x sigma prime. Let us see how all this helps in the discussion of the example of a blow-up from the beginning. So consider again the blow-up. As a map of fans, it looks like this, and our task was to determine the fiber of the origin, which is the limit point x sigma, in terms of this map of fans. We are going to apply our formula for the fiber. So, the fiber of this limit point x sigma. We have to look what are the cones such that the relative interiors map into the relative interior of sigma. Well, that's easy. It's sigma 1, rho 3, sigma 2. So we have these limit points in the fiber, in any case, but now we have to see what are the inverse images of isotropy groups. That's easy. In this case, sigma, x sigma is a fixed point, so the isotropy group is the whole two toros. So in all these cases we have just the two toros in front. This is good, because in this situation what is written here is the closure of the torus orbit through x rho 3. In that case, we know what is the fan. The fan of the orbit closure is obtained by projecting the star along our given cone. So in our situation, we have as a cone rho 3. The star has 2 more cones, these 2 maximal ones, and if we project along the linear space generated by rho 3, we end up with this picture. So the fan of our orbit closure, which is the fiber, is the fan of the projective line as we expected. See you in the next clip.